Good morning everyone. I am Tanushri Dhalai from Civil Engineering branch. So in the last class we completed this numerical up to the suitable section, and after that we continue this up to the properties of the suitable section. So these are the properties of the suitable section that we got as ISMB 300 at the rate 433.6 Newton per meter. So now, as per the procedure, we have to find out the epsilon value. The formula is 250 by Fy whole root over. Hence, the value we got 1. So now, we have to put the conditions from the table number 2 in IS code. So now we have to find out the B value. So B value we can find out by the putting value of BF divided by 2. So the BF for the suitable section is given as 140 and 140 by 2 equal to 70 mm. So now we got the value of B as 70 mm. So now we can put the value in the first condition, that is B by TF. So B value is 70 and TF value is 12.4. So that is 5.64. So now we have to compare this with the value of the condition. So you can see the 5.64 is less than 9.4 epsilon. That is 9.4 only, because we know that the epsilon value is 1. Hence, it is belongs to the plastics cross-section type of the beam. Then the second condition is D by TW. So first of all, we can find out the D value from this formula, which is H minus 2 into TF plus root radius. So the H value is 300. And TF value is 12.4 and root radius value is 14. So by putting this value, we got the D value is 247.2 mm. So now we can put the D value here. So 247.2 divided by TW, that is 7.5, which is equal to 32.96. So again, the 32.96 is less than the value 84 epsilon, that is 84. So here also we can find out the beam section belongs to plastic section type. So now we can write the section is considered as plastic section. So now we forward to step 5. Here we have to compare the ZP provided value. Hence we can find out whether the provided ZP value and the section type, that is the suitable section, is safe for the design or not. As we know that the ZP provided value is more than ZP required, hence the provided suitable section is safe for the design purpose. So that we can directly put the value here. So then step 6. So in case of step 6, we have to find out the design shear strength and shear stress. So now we have to calculate the design shear strength for the two types of loading system separately. So for the UDL, first of all, the W1 value, we know we have to add the self weight of the beam, as we know that the assumed self weight is 2.1 and the actual self weight of the beam is got from the steel table as 0.4336. So to convert it into factored load, we have to add 2.1 plus 1.5 into 0.4336. Hence the value is 2.533 kilonewton per meter. So now W2 is given as 390 kilonewton. So we don't need to add self weight with W2 because it is a point load, so that we don't need to add the self weight with the concentrated load. We only add the self weight with the UDL type of value. So now we can find out the design shear strength. Before that, we have to find out the V value, that is the shear value. So now for the UDL case, we have to put W1 into L divided by 2, that is the case of UDL, and W2 by 2, that is the case of concentrated load. So by putting the W1 value, which is this value, that is 2.5336 into 1.4 divided by 2, plus W2 is 390 divided by 2. Hence the total shear is calculated as 196.773 kilonewton. So now we have to find out the design shear strength, which is the step 7. So now VD is equal to Fy into A divided by gamma m0 into root 3. And to calculate the A value, we have to multiply two things, which is H into TW. So Fy is 250, H is 300, TW is 7.5, and gamma m0 we know 1.1 into root 3. Hence, we got the value of VD as 295.235 kilonewton. So now we have to compare V and VD and find out whether it is a low shear case or high shear case. So now, first of all, we need to check out this value, that is V is greater than or smaller than the 0.6 VD. So by putting 0.6 into VD value, we got the value 177.141. So by comparing this two condition, that is 196.773 is greater than 177.141. That means it is a case of high shear case, as V is greater than 0.6 VD case is satisfied here. So where we have to find out the MdV value after this. So to find out the MdV value, we need to know the MD value, beta value and MFD value. Okay. So we know the value by which we can calculate the MD, that is beta B into ZB into Fy divided by gamma m0. So we know that beta B value is 1 for the plastic section. Then ZB value we know 651.74, and by converting it into mmQ, we have to multiply 1000 here, and Fy value is given as 250, gamma m0 is 1.1, and this formula is given in page number 53 in IS code 800-2007. Hence, the MD value we got 147.89 kilonewton meter. Now, we have to find out beta value. So, beta value is 2 into V by VD minus 1 whole square. So, 2 into V value is 196.773, VD value is 295.335 minus 1 whole square, which is equal to 0.110. And now comes to the MFD value. So, MFD value is equal to ZFD Fy divided by gamma m0. Again, we have to calculate the ZFD value. So, ZFD value is equal to ZP minus TW into H square divided by 4. So, ZP we got as 651.74 into 1000 minus TW is given as 7.5, H value is 300. By putting all this value, and we got the value of ZFD as 8482990 mmQ. So now we can put this value in the equation 2. So by putting this value, we got the MFD value as 109.770 kilonewton meter. So now we got the value of MD, beta and MFD. So now we can put all this value in the equation 1, which is MdV. So by putting all this value, we can find out the MdV value. So now by putting MD, beta and MFD, we got the value of MdV as 143.696 kilonewton meter. So now we have to find out the conditions, whether it is satisfied or not. So the condition is 1.2 Jd Fy by gamma m0. So Jd for the suitable section is given as 573.6, and by converting into mmq we have to multiply 1000 here. So 1.2 into this one divided by 1.1, we got the value of condition as 156.436 kilonewton meter. So now you can see the 156.436 kilonewton meter is greater than MdV value, that is 143.696 kilonewton meter. Hence the condition is satisfied. So we can say that the suitable section is safe for the design purpose. So last one, which is the step 9, that is the check for the shear or the check for the deflection. So we know that while we have considered the deflection part, we need to apply the working load here and exclude the self weight of the beam. So in the first step, we know that the W1 value as the working load is equal to 1.4 kilonewton per meter and W2 value is given in the question as 260 kilonewton. So the total deflection is equal to the deflection for the dead load plus the deflection for the live load. So here in the UDL part, we have to put the 1.4 kilonewton meter, and for the concentrated load, we have to put 260 kilonewton. So now we know here we have to put the working load. So 5 into 1.4 into 1400, that is the length or the span of the beam, to the power 4th divided by 384 EI. So Young's modulus, we know that for the steel section 2 into 10 to the power 5 Newton per mm square, and I value is given for the suitable section as 8603.6 into 10000. So now for the point load, that is 260 into 1000 into 1400 to the power q divided by 48 into 8603.6 into 1000. So by putting all this value, we got the value of deflection as 0.867. So now we have to apply the condition, that is the L by 300, and check out whether it is safe or not. So L value is given as 1.4. So by converting it into mm, we have to multiply 1000 here. So 1.4 into 1000 divided by 300 is equal to 4.66. So you know that, see here, the 0.867 is less than the value of 4.66. Hence, the provided section and all the checkout and design procedure is safe for the design of beam. So in this way, the numericals regarding the beams is completed. So today this much. We will solve another problem regarding the beam section in the next class. So today this much. Thank you.